Hey everyone, today we're going to look at the last lesson in Unit 6 on the dot product. We're going to explore one of the ways that vectors can be multiplied. That's through the dot product of two vectors. When we use the dot product, our answer or our result is a scalar. It's not a vector. So the dot product of two vectors is not a vector, but it's a real number. Another method of multiplying vectors is known as the cross product, but that is a vector that's perpendicular to the plane and the two vectors being multiplied. This takes us into 3 dimensions, so it's outside the scope of this chapter. So let's look at the operation of dot products. A dot product of a vector u and a vector v, you notice that we multiply the a components and then multiply the b components and then add those two products together. Here's some properties of dot products that you can refer to on your homework or as you need. Another consequence of dot product is that we are able to use the dot product in order to find the angle between two vectors. One formula is this one here at the top. Cosine is the dot product of u and v divided by the product of the two magnitudes of the vector. And then if we rearrange this equation, you can find an alternate form of the dot product here. The dot product is the two magnitudes multiplied together by the cosine of the direction angle. And then orthogonal, if you've never seen that word before, orthogonal means perpendicular, and perpendicular can also be called normal. So orthogonal, normal, and perpendicular are all the same meaning about two vectors. And we have perpendicular vectors if the dot product is 0. So that's one little test that you can use to determine if two vectors are perpendicular to each other. So let's get started. Here we have in example 1, we want to use the dot product, and we said that the dot product is between two vectors is multiplying the a terms together and then multiplying the b terms together and then adding those sums. So in this case, the dot product of u with v is 5 times -3 plus 12 times 2. So our dot product is -15 plus 24, which ends up being the scalar 9. So u dotted with v is 9. That's a scalar, just a real number, not a vector. Not a vector. It's just a multiplier, a scalar. In example 2, if we use the dot product to find the magnitude of 2, -4. So if I draw my vector 2, -4, so this is 2, and this is -4. This is my vector here. So I can use the dot product by doing u, the magnitude dotted with itself. So u dot u, and that would be 2 times 2 plus -4 times -4, and that is 4 plus 16. So if I want to get rid of the square, I could take the square root of both sides, and then the magnitude would be the square root of 20, but that has a perfect square inside, which is 4, so square root of 4 is 2, and 2 square roots of 5 would be the length or the magnitude of this vector u that goes from the origin to 2, -4. Okay, so dotting a vector with itself would give us the magnitude. Here's one with perpendicular vectors. So these are orthogonal vectors. We want to prove that. So to prove that, we said if u dotted with v equals 0, then our vector u would be perpendicular to v. So we want to test that out. What is u dotted with v? That would be 2 times 3 plus -1 times 6. And we can see that 6 minus 6 equals 0. So u dotted with v has a dot product of 0. Therefore, u is perpendicular to v. And we have shown that using that property. On to example 4, we want to find the angle between the two vectors using that formula. And let's just write the rule over here. They said the rule was if we want to find the angle between two vectors, we want to take the dot product in the numerator and divide it by the product of the magnitudes of the two vectors. So our one vector is 2, -1. So this is the first vector, u. And I'm going to use that little tool we had to draw the vector in a nice straight line. And the other vector is 6, 4. So that would be located up here, 6, 4. And we want to find that angle between these two vectors. So we need to know this angle here. That's our direction vector, direction angle. So putting that all together, the cosine of the angle will be u dotted with v. So that's 2 times 6 plus -1 times 4. And we're going to divide by the magnitude of the two vectors. So the magnitude of u is going to be 2 squared plus -1 squared. And then the magnitude of v is going to be 6 squared plus 4 squared. So cleaning that up, we've got the angle would be cosine inverse, and our numerator is 12 minus 4, and our denominator is going to be the square root of 5 times, 36 plus 16, so the square root of 52. And to make it even easier on us for the calculator, we're going to combine terms. So I want to enter 8 divided by square root of 260 on our calculator. Okay, so let's see. Look, we've got cosine. Make this smaller a bit so I can lock that down. Okay, cosine inverse. We need a fraction. 8 in the numerator. And radical 260 in the denominator. And then converting that radian, multiplying by 180 and dividing by pi, we have an angle of about 60.26 degrees. So our angle is roughly 60.26 degrees. Okay? So that's pretty simple for that way. Excuse me. Now, before we look at example 5, we saw the refrigerator problem in the last lesson. This is similar to that. Finding those components. So if you want to decompose a resultant, so that force F is our resultant. It came from adding force 1 and force 2 together. And if we did that, how could we find those component parts? And this is with the crate. So I'll let you read that story. But basically, it's similar to what we did in the last lesson. Let's say we have angle or vector u and vector v, and they're two non-zero vectors, and they have the same initial point P. And if we wanted to find vector u, we could do that by adding component 1 and component 2, because they're the orthogonal or perpendicular vectors. W1, notice, is parallel to vector v, and vectors 1 and 2 are vector components of u. So this is known as the projection of vector of u onto vector v, and it's written this way. If you wanted to know the component for w sub 2, it's given by u minus w sub 1. So if we take u and subtract this one, we would know the length of this one. And then this is just a slide of if theta is an acute angle, if your angle is an acute angle between u and v. And this one is if your angle between vector u and v are obtuse, then your w is outside of that vector. Excuse me a minute, I gotta get a drink. Okay, allergy season here in Florida. And you notice between the previous slide how this vector v was longer than vector u, but we had an acute angle. And in this case, our vector v is much shorter than vector u with an acute angle. So the component is that little extra piece that fills in, makes vector v long enough so that we can create that tip to tail or that parallelogram to add this component plus this component w sub 2 in order to get vector u. So what that extension would look like. And these are the 4 different formulas that we can utilize in finding components of vectors, whether it's the projection or the sum of 2 vectors to get u, or the difference of 2 vectors to get one of the components. So let's use this as our example. If you're given u is 4i plus 2j, and vector v is I plus 2j, we want to find the projection of u onto v. Got a little extra addition sign there. Okay, so over here on our picture, we can label this up a little bit. 4, 2 is this vector here. This is vector u. And vector v is 1, 2, so this little blue vector is vector v. So this extension, this red piece here, is going to be our component w sub 1, and then this distance is w sub 2. So we have to find the lengths of all of those. And we're going to start off by saying w sub 1 is the projection of u onto v. So that's the dot product of u and v. So we want a dot product 4 times 1 and then 2 times 2. So 4 times 1 plus 2 times 2 gives us that numerator. Then we want the magnitude squared of the denominator, and we're multiplying by the vector. Okay, so we're going to multiply by the vector 1, 2. And then the magnitude on the bottom is going to be 1 squared plus 2 squared, and we're going to square that when we're done. So w sub 1 is 4 plus 4, so we've got 8 in the numerator, and this is the square root of 5 squared, which gives us 5, and we're multiplying times 1, 2. So w sub 1 has components 8/5 and 16/5, which means if you look at it, 8/5 is 1 3/5, so you come out here about 1 3/5, and you go up 16/5, so 1 3/5, and go up 16/5, which is 3 and a little more, 3 1/5. So not too bad for drawing it. Now W sub 2, to get W sub 2, you have to take vector u and subtract the component that we found. So W sub 2 is vector u, which is 4, 2, and we want to subtract 8/5, 16/5. So a little 5th grade math here. You good at 5th grade math? We're going to change 4 into 25ths, and we're going to change 2 into what, as 5 is what, 10/5? 10/5. So we've got that to subtract from this. And I didn't mean to put a minus sign there. I meant to put a comma there. So this vector minus this vector, so 25ths minus 8/5, because we want to compare the A to the A and the B to the B. So 20 minus 8 is 12/5, and 10/5 minus 16/5 is negative 6/5. So this is my W sub 2, or component, the second component, which means we would go out what, 5 is 2 2/5, 2 2/5, and go down negative 6/5. That's this one, isn't it? So this is W sub 2. W sub 1 finished off my vector that created that length. And W sub 2 was the diagonal to get our resultant. So components of a vector, breaking them apart into each piece. Those will come in handy in physics when you're figuring force and things like that. Here's an easy physics problem. Let's say Randy is pulling his niece Rachel up a driveway with a grade of 15 degrees, and Rachel weighs 80 pounds. We want to know what the magnitude of the force is needed to keep the wagon from rolling down the driveway. So the force of her weight is 80 pounds, and it's going in the y direction, so that would be negative 80j. That's this, her weight. And W is going to be our vector with the angle 15 degrees. So we've got cosine 15 degrees in the I direction and sine 15 degrees in the j direction. Okay, so if I want to find V, I would do the force of her weight dotted with W, and then the magnitude of W squared times W. So this square would get rid of that W, and V would be negative 80, so the J and the J, sine of 20 divided by W, so that would be what, cosine, the square root of cosine 15 degrees squared plus the sine squared of 15 degrees under the radical. So we need our calculator again. And we'll clear that off. We've got a fraction with negative 80 times the sine of 20 degrees in the numerator. And in our denominator, this is a little trickier to put in there. Square root, I need a set of parentheses for the cosine of 15 degrees, and then outside that parentheses we want to outside the second set of parentheses, we want to square the whole thing. The cosine of 15 degrees squared plus a new set of parentheses with the sine of 15 degrees, and then again get outside of both sets of parentheses and square that. So we've found that W value 27.3616. So we got negative, whoop, I lost my calculator, need that. Negative 27.3616 times the cosine of 15 degrees in the I direction plus the sine of 15 degrees in the J direction. Oh, my writing's up here not so good. Let's see. Yes, so W would be the magnitude. We needed the magnitude. Got carried away there. So W times this vector is that magnitude times the cosine of I plus the sine 15 of J. So this is our vector. What's the magnitude of the force? So the magnitude of the force, let's say it in a sentence, magnitude to keep Rachel in the wagon from rolling down the hill is 27.362 pounds. So right about 27 pounds. So a fairly easy physics problem. And then here's two more easy physics problems talking about work. In physics, the work we do, W, by a constant force F in moving an object from point A to point B is defined as magnitude of the force times the distance. And you can find work either by the projection of F onto PQ times the magnitude of the vector, or the force times the vector times the cosine of the angle, or force times displacement, or magnitude times displacement. So the first one is that simplest formula. Work is the force times the displacement. We want the work. How much work, energy does it take to move a 30-pound bag of feed, and we're going to lift it 25 feet in the air. So our cosine, if you're lifting a 30-pound bag 25 feet in the air, you got 25 feet to go, and this is some 30-pound bag of feed. You notice that my angle is 90 degrees. So that's sine, and the sine of 90 is 1. So our answer is times 1. Since we don't have a cosine, this is a sine. So work is 30 times 25, which is 750 foot-pounds. And foot-pounds is where we get torque from. A foot-pound is about 1.4 joules. And it's a unit of work or energy. And here's our last one. If a child is pulling the sled along the level ground by exerting a force of 26 pounds on the rope, so here's my rope, it's got a force of 26 pounds, we're going to call that magnitude. And the rope's making a 34-degree angle with the horizontal, so if you think about this being 34 degrees here, we want to know how much work does it take to pull that sled 225 feet that way, right? We need to go 225 feet on the horizontal. So one of our formulas said work is the magnitude of the force. Oh, we got it right there. I'm not going to rewrite it. We're going to use magnitude of the force times magnitude of the vector times the cosine of the angle. So in this case, we got work is the force, 26 pounds on the rope. The vector length we're moving is 225 feet. And in this case, we've got an angle, cosine, on the x-axis, 34 degrees. So again, we need our calculator. And 26 pounds times 225 feet times the cosine of 34 degrees. And it takes the work to be done, or the energy is about 4,800, I'm going to round it, 4,850 foot-pounds. And if you want to make a note about what a foot-pound is, just for your own knowledge, since our units are foot-pounds, 4,850. 1 foot-pound is about 1.356 joules. And it's a unit of work or energy It's the energy that's transferred. Oh, I'm going to run out of room here. On applying a 1 pound force through a 1 foot of displacement. So let's move our work out of the way so we can write that down. It's the energy transferred on applying 1 pound of force through 1 foot of displacement. So as you pulled at 1 foot and applied 1 pound, you'd get a foot-pound. So we need 4,850 foot-pounds to do all that work. And that, my friends, is the end of chapter 6. Bye.